Okay, this is a short video on sensory physiology, and I've just done this pre-recorded, and then you watch it. Hopefully, it will help. Now, sensory physiology, remember we have sense organs, these sense organs that are separate from somatic sensory organs, things like the human ear, we have the human eye, we have the taste buds, we have the semicircular canal, the one that performs equilibrium and balance. But for now, I want just to focus on vision as a part of sensory special senses. So let's get to it. Here we have the human eye. This is the sense organ. We call this the sense organ. And of course, it's concerned with conversion of electromagnetic energy into electrical energy that are then taken by optic nerve all the way to the brain for perception. Now, the human eye, we can see it's divided into two main parts. From this part where there is the laser up to this part where we have the retina. Retina is excluded. So the cornea, aqueous humor, lens, vitreous humor, all these constitute what we call the optical eye. It's just the optics. It doesn't do the seeing, it only does the direction of the light into the fovea, or where we have the photoreceptors. That's the main purpose. So we have the cornea here. This is the first element that forms an interface with the atmospheric air. Now, if you compare the atmospheric air and cornea, you'll find that atmospheric air is less dense compared to cornea. And this is why we usually say that cornea is the one that refracts light the most, because light is actually moving from a less dense medium to a denser medium, and therefore the refraction, it will be greater at the cornea. Then from cornea, we have what we call the aqueous humor. Remember, this cornea, it's usually avascular. It's not supplied by blood vessels, so it depends actually on the aqueous humor to get its nutrients, to get its oxygen, for it to thrive. And this aqueous humor is usually produced by the ciliary body. Remember, it's produced by this ciliary body, and then it passes all through posterior chamber, this posterior chamber of the iris, and then it gets into the anterior chamber, and then it's usually reabsorbed at this point. And this point we usually have trabecular meshwork, or also you can call it the canal of Chalem. I don't know if I'm pronouncing it okay, but it's usually reabsorbed here. So sometimes this iris can actually close this point of reabsorption, and it may cause accumulation of this aqueous humor, and this may lead to increased intraocular pressure, what we usually call the glaucoma. You feel it's usually very painful. Then from there we have the lens. Now the lens, it's the one that has a physiologically adjustable refractive index. It can actually change. It can become more globular. This one make it refract light, especially when you are looking to a near object. But if you're looking at a far object, it becomes almost flat. It becomes less globular. And remember, the anterior aspect is the one that has more space for the changes of the lens. This anterior aspect of the lens is the one that has more space for accommodation, not the posterior part. So during accommodation, that's the changing in the globosity of the lens. It's actually the iris and the anterior aspect that are moved. Then from there, you can see these are zonules. These zonules, they are the one that can change the shape of this lens to allow accommodation. And then from there, we have vitreous humor. Vitreous humor also participate in refraction. It also refracts light and help foveating this light into the fovea. Then that's actually the end of the optical eye. The rest here, it's actually the retina, and the retina is actually part of neuronal eye, which contains the receptors, and then the photoreceptors, and then of course bipolar cells, and then from bipolar cells we have ganglion cells. Then the ganglion cells are the ones that actually form the optic nerve, and then the optic nerve takes all this signal to the optical brain. So that's in brief how this human eye is. And then now let's come to the neuronal eye. Now this is the neuronal eye. Of course, you can see these. We have the pigmented layer. This is the pigmented layer, and this one usually absorbs light. Remember, light usually comes from this direction, and then it hits the pigment. It absorbs that light, so that there is no reflection. Remember, it's dark pigmented layer. And then we have the rods and we have the cones. You can see the rods. Ideally, from the architectural design, you will see that we have many rods synapsing with one bipolar cell. But if you look at the cones, it's actually one on one. One cone on one bipolar cell. And this is so good because here we have a very it enhances the cones. Remember, it's for detail looking. Detail, we need what's the best name? Detail description of an object, the color, the contours. You need to get all these details. So for this purpose, you can see the receptive field is different from that of rods, so that it can increase the resolution. The resolution is actually good when we have one cone, one bipolar, and then all the way to the ganglion cell. But for the rods, this one are actually made to optimize vision in darkness, for scotopic vision. That's why we have many rods synapsing with one bipolar cell. So if each rod take some minimal amount of light in darkness, they can actually optimize because they are all converging in one bipolar cell, and then it all go to the ganglion cells. And then the other thing, the cells that you need to know, that the photoreceptors, they're actually synapsing with what? Bipolar cell, and then we have the horizontal cells here, and then we have the amacrine cells. Then from amacrine cells, bipolar cells and ganglion cell synapse, and then it's actually the ganglion cells that forms the optic nerve. These are questions that they like asking, that which one of the following cells usually forms the optic nerve. It's usually the ganglion cells. Then in terms of the differences, you need to know the differences between the cones and rods. You can see rods, of course, they're actually called rods because they have that shape. They have this shape like a rod. And then this one, it's actually conical. Then rod, they're actually for scotopic vision, that is in the darkness. And then cones are for photopic vision, that is during the day. Color vision, all about that. Then resolution. Rods have poor resolution. Cones have the best resolution because it's actually one cone on one rod. Okay. And then in terms of synapsing, we have many rods synapsing with one bipolar cell, but we have one cone synapsing with one bipolar cell. The other difference that you need also to pick is the pigment. The cones usually have photopsin, and they have three types of cones, but rod usually have scotopsin. They have scotopsin. scotoptin. Those are differences. Of course, there are many other differences that you need to know, but that one is just for today. Then the neural pathway. Now, the neural pathway, remember we said that we have ganglion cells forming the optic nerve. Now, the last thing we are seeing is the ganglion cells because they are the one that form the optic nerve. Now, we have the temporal, that's from this side. These are temporal part. Then this is the nasal part. Now, from temporal part, you can see the optic fiber passes without dicassating. Dicassating is crossing over. So from temporal fibers, they are ipsilateral up to the thalamus. Remember, it's the lateral geniculate body of the thalamus. And then the synapse there, and the synapse there with geniclo-calcrine tract. Then the geniclo-calcrine tract, they take those signals up to the occipital lobe. And then the nasal fiber is from this point, this here closer to the nose. The nasal fibers, you can see the nasal fibers are dicassating. The one from right eye goes to the left, and the one from left goes to the right until to the thalamus, and then from thalamus we have the geniculocacrine tract all the way to the occipital lobe. Now, because of this, if there is some lesions, then it affects the vision differently. Let's say part A is damaged, the part that is lightly colored, if it's damaged. So if where my laser radiation is damaged, then we shall have blindness, monocular blindness. That's the blindness of the left eye. Because all the fibers in that side are affected, they cannot transmit to the brain. That's why we have this kind of blindness that we call monocular blindness or blindness of the left eye. If it was here, then it would have been the blindness of the right eye. Then we have point B. Point B, it's very important to know because this is the point where we have what? We have the pituitary gland just closer there. So if we have a tumor of the pituitary gland, these fibers are the one affected. And you can see they are the fibers that are dicassating. And we've said the fibers that are dicassating are nasal fibers. So the nasal fibers cannot take their signals to the brain. And this will form what? This one will form B. You can see what we call the bitemporal or heteronymous hemianopia. Heteronymous hemianopia. And then we have part C. If part C is tampered, you can see it's both this side and the nasal of this side that are affected. So we shall have right homonymous hemianopia. So the right side will be affected. Then D, you can see D now it will affect the macula. So the macula will not be affected. You can see this that point, this indentation. That's what we call the macular sparing. The macular sparing. So that is it. Those are the pathways, but the idea here was to know this pathway. From ganglion, the temporal fibers do not dicassate, nasal fibers dicassate. Then the temporal fibers are ipsilateral up to the thalamus. Which part of the thalamus? The lateral geniculate body. Then from there we have geniculo-calcrine tract. Remember there is a calcrine fissure here. So it's connecting this geniculate body and the calcrine. That's why we're calling it geniculo-calcrine tract. So remember that for you. The other thing, this still we have already discussed. You can see the small receptive field for the cone and the large receptive field. Because of this, we have better resolution with the cones and then very poor resolution with the rods because of this large receptive field. The accommodation, this one I already talked about. Remember I said it's actually the anterior part. You can see for the accommodated lens, the dotted area indicates where the iris is. If you're looking for a near object, something closer to you, you can see the displacement of the iris to allow the globosity, these lens to become more globular and refract light the most. Then we have this element of physiology of pupillary reflex. This is when you apply light from the eye, we have the changes. The pupil constrict. And in darkness, the pupil usually widen. So what's the physiology of this? So the physiology is simple, is that it involves the ocular nerve, that's cranial nerve number 3, and optic nerve. So when there's too much light entering the eye, that's via the optic nerve, cranial nerve number 2, it goes all the way, of course, to the occipital lobe, but there are some fibers, they usually go to the pretectal region. And then within the pretectal region, we have the nucleus that is concerned with cranial nerve number 3. That's the Edinger-Westphal nucleus. So if there's too much light, there will be stimulation of this interneuron. And this interneuron will stimulate the Edinger-Westphal nucleus, which is the nucleus of cranial nerve number 3. And remember, the cranial nerve number 3 has a parasympathetic part. So this one will enhance parasympathetic activity. And whenever you increase parasympathetic activity more than the sympathetic, then we have the constriction of the pupil. And this will limit entry of light, too much light in the eye. This is what we call pupillary reflex. So there is too much light entering the eye. It's taken by the ganglion axons, which are optic nerve. Then some of the fibers goes to the pretectal area, and within that area we usually have the Edinger-Westphal nucleus, the nucleus of cranial nerve number 3, the parasympathetic bit of it. So once you stimulate this nucleus, then you stimulate the parasympathetic fibers. Then there will be too much of parasympathetic activity more than sympathetic, and this will cause the pupillary constriction to limit the too much light entering. Then there's some visual abnormality here that we can see. We have the normal eye. You can see it's being foveated. The rays are foveated. Then hyperopia, where we have this the long-sightedness. You can see the foveation. It's actually beyond uh, the, 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 the beyond the retina. Therefore, the vision won't be good. Myopia, we can see the vision is in front of the retina within the vitreous humor. So for you to correct the hyperopia, you need a biconvex lens, which will converge these rays and help to foveate it. Once foveated, the vision will be good. But for this one, we need to push these rays further, and we use the biconcave lens, which diverge up to the retina and help foveating. This one I hope you did in your practicals. Then we usually have a lot of activity before the retina, the photoreceptor act. So remember we have this rhodopsin, and rhodopsin is not active. We need to activate rhodopsin so that we can the receptors, photoreceptor can respond to light. So the activation, remember we need this light. What light does is to isomerize this 11-cis-retinane. Remember the rhodopsin is simply 11-cis-retinane with scotopsin. Scotopsin is actually the pigment. So at rest or in darkness, it's usually 11-cis-retinane plus scotopsin. But we want to separate and activate the rhodopsin. So we need light. So light will isomerize this. It will cause the photoisomerization. So we shift from 11-cis-retinane to all-trans-retinane, which is an isomer of 11-cis-retinane. So once you isomerize this, once you photoisomerize this, you separate it from scotopsin. So you separate it from scotopsin, and then the 11-trans-retinane will be transformed into what? Bathorodopsin, and then further it will be converted to lumirodopsin, and then metarodopsin 1, and then metarodopsin 2. Now metarodopsin 2, remember this, is the active form of what? Rhodopsin. Now this one will activate now the transducin. And then transducin, remember, is a G protein couple receptor, is the one that now will activate the photodiesterase enzymes, which will now start breaking down the element within the cytosol. But to return to rhodopsin, we need vitamin A. Remember, we need vitamin A so that we can replenish this 11-cis-retinane to all-trans-retinane. This vitamin A is usually mostly stored in the pigmented layer. So it will be transformed to 11-cis-retinane by presence of what? We shall return back to 11-cis-retinane 1 by presence of vitamin A. In absence, then this is what brings what? What we shall refer the night blindness because of absence of vitamin A. So once we have 11-cis-retinane, it will recombine with the scotopsin and then form rhodopsin. So let's see this from here. Metarodopsin 2 activate transducin, and then transducin activate photodiesterase enzyme, which now we come here. Remember, we have the rhodopsin. There's a lot of steps we talked about. Remember, light simply transform rhodopsin to metarodopsin 2. Then metarodopsin 2 activate the transducin. Transducin is a G protein couple receptor. And then this one now activate the cGMP photodiesterase, the PDE. So once you activate this, it will start breaking down the cGMP to 5-GMP. And therefore, we reduce the amount of the cGMP. But once we reduce this level of cGMP, remember they're the one that open the sodium channel. So they will close the sodium channel if we reduce it, if we shift to this side of 5-GMP. We reduce the cGMP that open this sodium channel, and this now will start causing the hyperpolarization. Remember, we usually say that the photoreceptors are the only receptors that respond to their stimulus not by depolarizing, but rather by hyperpolarizing. It's because of this. Because the photodiesterase simply reduce this, it breaks down them further to 5-GMP, and therefore the sodium channel close, and this will bring about hyperpolarization. Further explained, you can see sodium channel closed. In darkness, we have this dark current because we are not breaking down the cGMP. But in light, we are breaking it, so there is no sodium channel. So this is what we usually call the dark current. In light, no dark current, because the sodium channels are closed. Now, these are the photoreceptors here. You can see, we've said photoreceptors hyperpolarizes. You can see, once there's light, they hyperpolarize. And then they are connected to bipolar cells. And then also we have the horizontal cells. The horizontal cells also hyperpolarizes. So the only cells that hyperpolarizes it's photoreceptors and horizontal cells. And then bipolar cells, they can hyperpolarize whenever photoreceptor hyperpolarizes, and they usually also depolarize. And then the amacrine, these now are the ones that act like generator potential. They are that generate the receptor potential. So whenever they reach threshold, it's when the ganglion cells depolarize. So the only cells that have action potential is the ganglion cells. Amacrine is simply generator potential, and then ganglion cells can depolarize and then initiate action potential that are taken to the occipital lobe. Color vision. Remember, color vision is by cones. Now, cones, they usually make this, of course, this is the transducing, the photoreceptor, the photopsin. And remember, we have three types of cones. These cones, of course, the photoreceptors here, the receptors here, they are made by the nucleus of this cone. So we have chromosome X usually make the opsin for we have these three: red cone, green cone, and blue cone. So this is the long wave. Red cone is the long wave, you can see, and remember, the longer the wave, the lower the energy. And then we have medium wave. This is the green cone. So we have opsin 1, long wave, opsin 1, that is medium wave, and then opsin 1, this is short wave. The blue cone, it usually has the short wave wavelength, that is. So if the wavelength is short, then it's very strong. It has more energy. It has more energy. So what happens here? Remember, the first two are made by X chromosome. And this is actually why the color blindness is usually most common in men. Why? Because all these are on the are on the are on the X chromosome, but blue cone is actually in chromosome 7, which is rare. You rarely have someone with color blindness related with the blue cone. So if someone has issue with the red cone, we usually call it protanopia, red color blindness. It's on the X chromosome. Then if someone has issue with the green cone, then we call it deuteranopia. That's the green color blindness. These are the most common, and mostly men are affected. Then for blue cone, which is rare, is tritanopia. Then the other thing is to know is that within the brain, the Brodmann area V8 is the one responsible for color vision. They like asking this, that which Brodmann area is responsible for the color vision. It's usually V8. So lesion of V8 will cause color blindness. So these are electromagnetic energies. Remember, the light from the sun is usually white, but it's a composite. It has several colors. So if we place a prism, we can separate all these colors. So white simply means a composite of several colors, and you can see this rainbow here. The red, orange, yellow, green, blue, and violet. But we have the receptor for red, green, and blue. So as you go down, the wavelength reduces. So there's this joke that was said by the then president, the president of Uganda, Yoweri Museveni, that South Sudanese usually appear blue rather than black, which there's some element of truth, because we've said that the blue has a short wavelength, so it's very strong. So when it hit on the surface of a blue South Sudanese, not all is absorbed. Remember, all these need to be absorbed for us to see the black. But if the blue, because it's strong, some will be reflected, and it will stimulate the blue cone, and then they'll have that blue tinge of color. So this from theory of what? Trichromatic theory, or also you can call the Young-Helmholtz theory, which states that the color we usually see depend with which cone we stimulate. So if you stimulate a red cone, then you see a red color. If you stimulate a green cone, then you see green color. If you stimulate a blue cone, then you see the blue color. If you stimulate all these cones, then you see black. No, 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 no. If you stimulate all of these cones, then you see white. If you fail to stimulate any of these cones, then you'll end up seeing uh, if you stimulate all of them, black. No, white. If you fail to stimulate any of them, then that is black. So it's simply a combination of those that bring about the colors we see. So this is the brain, remember V8, this is the occipital lobe is for vision, but the one that is concerned with the color is the V8. Remember that, V8. So you can see here it's V8 is for color vision. They like asking this, you better know that. And then V1 is for primary visual cortex. So I have here a set of questions. One of the following area is uniquely concerned with the color vision. There it is. We have D as our best answer. Then pituitary gland tumor is likely to cause one of the following visual deficit. Remember, it will compress the dicasseting fibers, and the dicasseting fibers we've said are nasal fibers. So which one is likely to be caused here? It will be heteronymous hemianopia. So that is that. Then the active form of rhodopsin is that is metarhodopsin 2, the one that activates transducin. Then the optic nerves are formed by one of the following cells. This one, of course, is the ganglion cells. They're the one that the axons of the ganglion cells forms the optic nerve, cranial nerve number 2. Then one of the following optical part of the eye has the highest refractive index. This one, of course, there is no answer here, but more of lens. I think the answer should be cornea. Cornea. Cornea is the best answer there. I think that's the end. Thank you so much. You'll watch this and then maybe prepare for your exams.